So I'm Thorsten Liebig. I'm part of the management and project team at Derivo. Derivo is a small company in Germany that helps other companies and organizations in facing the challenge of more and more distributed, complex, and heterogeneous data with the semantic management of this data, and that always includes graphs. So what we typically do in our projects, we turn data into a graph and then add semantics and reasoning to that graph. And so in our perspective, it's not a decision of whether to use labeled property graphs or the RDF data model, because they're so close related and there's a smooth step just from one model to the other. It's more a question of how much knowledge I would like to have in my graph. And I will elaborate on that in my talk with the help of two industry use cases. The first one is from the automation industry. So we are on a project with a large German automation manufacturer. And whenever you have something to move, to push, or to press, they have a solution for that. And that's typically done by basic components such as these, which are parts of electrical drivetrains, for instance. Here we have an axis. There you see a mounting kit that connects an axis to a motor. We can optionally have a gear, not shown here, and a controller. So from these basic components, you can build drivetrains, millions of different combinations of these components, and these combinations is built by compatibility. So they have, or they maintain interfaces that tell the compatibility between motors and controllers, for instance. So whether they have the same voltage, whether there is a cable to connect them, and so on. So many interfaces. And whenever these two interfaces are compatible, then you can combine them in order to build such a drivetrain. And then you can build even more complex systems. Think of a 3D portal that is a pick-and-place solution for picking something up and placing it in a factory. Here, they don't allow it to combine any drivetrain with any other drivetrain to build such a Cartesian system. So there are constraints either by product management, but also from engineering. So, for instance, you don't want to have motors of different motor technology within such a complex system. So, how do they did that before we added graphs to the solution? So they had many tables containing information about these components, and tables about interfaces, and tables about which interface combines with which other interface. So in order to build all the drivetrains, they had to do many complex joints to come up with again tables that contained these drivetrains. And again, to build the more complex systems, you again have to do joints, and they also needed some external procedures that took the constraints into account I mentioned before to come up with one large table containing all the Cartesian systems. And that table even was too large to be exported into configuration applications for customers to download, because it's just too much data. So if you look on this as a graph, then it becomes much more easier. Here, think of these nodes as being motors of a drivetrain, and these nodes as being mounting kits, gears, motors, and controllers, potentially having properties such as technical data about these components. And then, just by computing the direct compatibility with the help of the interfaces, you end up with something like this. You even can have the interfaces in the graph as separate nodes, and we actually did that, but for the sake of the demo, I just let them out of the graph. Now, computing a drivetrain is as simple as a force hop graph traversal. So in order to find out which are the drivetrains which can be built with this particular axis here, you just follow the graph from axis to mounting kit, gear, motor, and so on. And you can even model complex systems. So just by adding more nodes that represent one dimension in such a 3D portal that refers to all the components which are within one dimension, and then connect that with other dimension, and so on and so on. So in the end, you end up with several thousand nodes and edges, which previously has been done with large tables, gigabyte of table space, and computation resources. So the process before took 1 to 2 days to compute all the systems. We reduced that to a small graph that provides the answer within 2 seconds, basically. And that's a picture of the graph that was built by the components. Here you see, I think these are controllers which are very heavily connected to motors, and there are mounting kits and other stuff. Another use case is from the logistics domain. We had a project with a large automotive supplier, and they produce products and materials, and they have to ship that to their customers, typically the car industry worldwide. So they have more than 1,000 shipments a day. And their problem was that they would like to do more analytics within their logistics domain to see, for instance, how many shipments do we have to Greater China above 1 ton initiated by some particular transportation distribution point. So we talked to them, and they explained their logistics domain, and we looked at the data, and at the end of the day, of the kickoff workshop, we came up with something like this on the whiteboard. So here you have the materials and the deliveries, which are made up of delivery positions that contain these materials. And there is a sender and a customer of this delivery, and the deliveries may be split up into units, which are then aggregated to shipments, and this data is distributed over different databases. And that again looks like a graph, basically. So here you have the materials, deliveries, they are related to customs and senders, and so on and so on. But if you look at the data, it looks more complicated, actually. So the deliveries are characterized by delivery numbers. So here each blue box is one delivery, basically, and the delivery items are those of this delivery are those which have a delivery item number and this delivery number. So these are the deliveries of this delivery items of this delivery, and this is the stuff of these delivery items, and so on and so on. So it's very complicated to do analytic queries with such a data layout. So typically you have to go to one IT guy, explain your query, they write the SQL query, come back with results, and if you're not happy with the results, you again have to talk to the guy, and he has to tweak his query. Because the structure, the graph structure is hidden here. So that's the delivery item of this delivery that contains this stuff, and there's even redundancy. So this is the same stuff number than this. So you typically end up in copying data throughout your whole table. So what was the typical workflow to solve this problem, to bring this data into a graph? So the initial situation is always the same. You talk to the domain experts and look at the documentation. You look at the data sources. You ask what kind of queries do you would like to ask. What are the relationships between your data? And then you come up with something what we call a graph schema, which basically is a set of labels for nodes and edges. So these are the relevant node labels and the relevant edge labels. So we're still in the labeled property graph world at this point. And then this is fed into kind of a importer component that uses this vocabulary to import the data and then to build the graph. And then you have the graph, and you could do querying with Gremlin or Cypher or whatever. But that's typically not the end of the story for the project we do. So we add more knowledge into the graphs. So what we do, basically, we build an ontology schema out of the graph schema. So how is it done? So typically when you talk to domain experts, they express things like, okay, if we query for motors, then stepper motors should also be in the result set. So there's a relationship between this label and this label here, which is, in terms of an ontology, a subclass relationship, which basically just tells everything that is a stepper motor also is a motor. Think of it as a rule that adds motor to a node as a label whenever there's a label stepper motor. And there are other relationships, such as axes and motors are drive train elements. So these both are subclass of something which is called drive link here. So what we typically do, we also add vocabulary here to better structure the data and to bring more levels of abstraction into the model. Another example is here for an edge. So if X is compatible to Y and Y is compatible to Z, to X, or Z, then X is also compatible to Z. So the compatible relationship or edge is kind of transitive. So that's something the domain experts perfectly know, but it's not explicitly given to the data. And think of the constraints from product management and engineering I mentioned before on the complex Cartesian systems. These are things which can be modeled as rules in the ontology schema. So that's something we call the ontology schema. So how is it done technically? What kind of tools do we use? We typically use Protégé as the tool for building the ontology schema. Here you can simply say stepper motor is subclass of motor just by adding this here as a subclass, for instance, or saying that compatible is a transitive relation is just by ticking this checkbox here. So you don't have to write any code for this. You just say this is a transitive relationship and delegate the computation to your ontology engine. So that's nice because it's on a very declarative level, which is easily to communicate to other people or to discuss between domain experts. Okay, so that's typically what we do from relational databases, and an ontology, in our understanding, is on a very abstract level, kind of a schema vocabulary plus rules plus the graph data. And what we typically use is the OWL2 RL fragment for doing that, because it is a very good compromise of expressivity and computational characteristics. So when you feed this ontology into an OWL engine, such a processing engine of ontologies, then this engine will add these links which follow from the transitivity characteristics, for instance, or add new labels to your graph. So you don't have to, you just delegate that to the engine, you know it's there as first-class data after you have applied the engine. So that's a way of making implicit knowledge into your graph explicitly available for applications that use this data. And then you can query it, and you can query for all these new relationships as well as for the told ones. And technically, these two components came within one system. So these are systems we are partially in charge of. So Conclude is a system that can deal with very expressive ontologies. In memory, we have a technology called GraphScale that can inject this kind of R2RL reasoning into any graph database or a triple store. And there's a system we often use, which is called REFOX, developed by colleagues here at Oxford Semantic Technologies. And the clue is to add the knowledge that is in the head of the experts, or that is just common sense, closer to the data, as opposed to implementing this within every application that uses the data. Okay, so now you have the data. That's one important step. Then you would like to query the data. You could use Cypher, for instance, or Sparkle, or whatever query language you like. For visualizing the data, tools typically offer this kind of network rendering, which looks nice when the data is below a threshold of nodes and relationships, but you cannot see anymore if you just have too much data. It doesn't help you. It looks nice, but it doesn't really tell you what is the relationship between this node and this node. Therefore, we have developed our own tool, which you cannot really see, but I will demo it in a second, which is an interactive, data-driven visualization and analysis tool that groups nodes according to its label. If you stick to the label property graph lingo, or class if you prefer the REF model. It aggregates relationships here, allows selective exploration, on-demand details, and filtering. And let me see whether I can do the demo with the mic in my hand. I can't. Can you just help me? Maybe we have to quit PowerPoint or the presentation mode. Okay, here we go. Okay, so that's the tool. I cannot show it with the data from the two use cases because that's confidential data owned by the companies. But here we have the tool with the data from the Panama paper data set, which basically also is a graph. We did the same for the Panama data as we did in the use cases before. Here you see what is called categories, which are either node labels or classes, if you prefer label property graphs or RDF. And here we have subclasses. So these here, for instance, the entities in Germany are those entities that are related to Germany. So that's something which has been derived by the OWL engine during loading because of the rules I mentioned before. And what you can do now is just to drag and drop that here into the visualization pane, and then you see this blue circle here that groups all these 241 entities in Germany. So each of the gray dots here is one of these entities. you can just click on it, and then you see details here on the right-hand side. And what you can do now, if you click on the plus here, then you see all the categories which can be reached by this group of entities in Germany. So you can reach addresses, 45 addresses, other intermediaries or officers, and if you hover over such a category, you see the relationships that are in between these two groups. So let's just go for addresses here. Then what you see is, okay, the dark gray ones are those which have a successor, which is an address. The gray ones, the light gray ones don't have one, and the number here tells that this address here is shared by 21 entities in Germany in the predecessor group, which is kind of interesting. You can mark that. Oops. So that's a kind of a nice finding, which typically our customers use this tool to find data flaws or other things which they don't expect in their data, or which are interesting in a sense that it's difficult to find with traditional Cypher or Sparkle queries. So what we can do now, we can do parallel exploration, say, okay, let's look for the offices of these entities in Germany, which you can see here, and then look, okay, what kind of entities are there? What kind of entities are there officers for? And then you see, okay, and as soon as the number of objects is below adjustable threshold, which you can adjust here, we don't show the individual objects anymore. So it doesn't make sense to show all these 9,000 entities. You can look at them just by going here into the detail view. Then it just fetches the detail information, and you can do filtering or whatever. Speaking of filtering, what you can do here, for instance, say, okay, I'm looking for a particular person. Let's say a person that, the name Peter. Here we find 6 of them within this 279. Apply this as a filter, and then what you see is that the filter propagates to the right-hand side. So you can do more filtering here just by using the facets of the dossier. So here you see, okay, these are the service providers of these entities, and if you go over some of these categories, you see them highlighted and can say, okay, let's say, okay, I would like to have the defaulted ones and the dead ones. Restrict the group to these. Then you see how you can drill down from a larger data set to data which is really easy to grasp and to understand. You can save all these groups here. So if this is an interesting group to you, you can just say, save this as a custom category, and then it also appears here in your list of categories. So while browsing the data, you can also refine your schema, your ontology schema, because this is just kind of it's like a rule you have defined here. A query interpreted as a rule, so it's perfectly can be interpreted as an OWL axiom, and then appears here in your category list. Okay, I think I have to sum up. So what's the conclusion? Semantic models increase the common understanding of the data and helps to integrate different data sets. It helps to find data quality issues. That's the first experience when you stick to a semantic data model. Then you see whether your real data really fits into that model, and if it does not, then either your model is not correct or the data has some issues. You can add domain knowledge by reasoning. I give a short example on that. Interactive visual analytics is the key for most of our customers. So they have large data graphs. They would like to see what's in there. They really don't know. They need tools like that to get ad hoc data insight, and especially in terms for SemSpec, that allows also to refine your model, which is a nice side effect. So what are the lessons learned? Business critical data always has some issues. I mean, that's always the case. Semantic modeling is not for free, so you have to invest into your model. It's not a push one button technique. So it needs some iterations with domain experts. It's not right there when you start modeling it, but it pays off in the end. And data exploration and querying is not only for IT experts, so I hope SemSpec provided a proof that even people not familiar with SQL, Sparkle, or Cypher can do sophisticated querying over their graph data. Thank you.
Any questions? Yes. So as far as I understand, the real intelligence resides with the humans, and only the tools support the humans in seeing the relationships between data. So as I saw with your tool in the last demo, the tool really only helps me to grasp the data and understand it better, and then I, as a person, refine the model.
Yeah, you refine the model while you, for instance, name nodes you find interesting when you name the nodes, they appear as categories in your hierarchy.
Yes, exactly, but it's not kind of machine learning?
No.
Input from the humans?
Yeah, sure.
And the machine just does rule evaluation and derive implications via rules that the humans...
Yeah, exactly.
I have one actually, which is not technical at all. So you said this solution was developed, you actually showed 2 use cases from different clients. Was it custom developed for those clients, or it's like a product that anybody can use?
No, it was developed before we just, the customers use this tool. In the beginning, it was developed as a tool for exploring large ontology data, but it also works for labeled property graph data, and yeah, it is available. The demos are available online, so you can check out www.semspec.de, and it's as soon as your data is either a labeled property graph or an RDF model, you can just load it right away.
What is your main storage data? Which form you keep the data? Is it RDF type store or quad store or in graph database, and then you look like on top RDF API?
At the moment, the SemSpec tool can work on different backends. We have a version running on Neo4j, for instance. So you load in the data as either RDF, or it's already in Neo4j as a labeled property graph, and then we kind of read out the schema by label inspection, and then you can explore it.
Over tabular data and not needing to go to get a SQL query written and that process. Where's the advantage coming from? Is the visualization in the interface that you build allows non-SQL writers to analyze the data? Or is it modeling it as a graph that gives that advantage?
It's both, I think. Modeling the data as a graph allows people to write queries more easily. I think it's more easy to teach somebody in Cypher and just saying, okay, give them a sheet that shows the overall structure, then they are able to write the Cypher query very quickly, as opposed to writing a SQL query.
Okay, well, thanks again.